So, okay, I'm going to solve this problem on the two problem in the exercise for discussion problem here. So let's see that. Consider the compound shown below. Predict whether the leaving group, so I'm going to pay attention to the leaving group, will favor SN2 or SN1. And so I'm looking at this. This is the essentially positive charge of the leaving group. And because it says a leaving group, so if they ever leave that, and it will be HOH, right? So H2O as a neutral. So based on that, I know this is a good leaving group because it's a neutral. It was charged as an attached side groups there. So when you have a good leaving group, this one will favor the formation of carbocation as it is. It is a unimolecular dissociation to form the carbocation. So that will be a single unimolecular step, unimolecular nucleophilic substitution. So that will be a SN1. So short answer for SN1, you are seeing the good leaving group, and that's the one that is related to this problem. As I mentioned in the beginning of my class before, the problem should designate whether it's a SN nucleophilic substitution reaction or elimination reaction. Otherwise, you cannot really solve the problem easily. So this is an elimination product. So they say, okay, this is an elimination reaction. Within the scope, I need to solve this problem. And so in the usual sense, this is a quote-unquote usual sense. Usually, okay, it's an elimination. So I know this is a base, and this one has a lone pairs electron, and it's an elimination. So this is a carbon. There is a carbon next to it. Should have a hydrogen. This will take the hydrogen or a proton as a base, and these two electrons will form the double bond here, and this bond will be pushed the chlorine away as a chlorine minus. So somehow you will have something like this, right? So this is an H, and then you will have a chlorine minus, and then you will have a ROH. So you can write an answer like this, but there is something more, and particularly we are going to challenging this question because there is some three-dimensional conformation of this molecule has to be considered, and this is about the geometrical accessibility, what I also call it as anti-approaches or the less crowded approaches, or the in a general sense it's called a steric hindrance. So to figure this one out, I need to essentially show this structure in a three-dimensional form to figure it out, how the structure is being formed. So let me try to do the first one. So this first one, I'm going to do the Newman projection here. Okay, so and then I'm going to put up blue dots, and then the ethyl is at the bottom, right? So this is on the plane, and then this one that's sticking out here, and that's a methyl. So this is a methyl that on your right hand side, and the other side is on hydrogen that you know. And then so this is what is on the front, and then we're going to change the color to the red, and this is what I mean. This is the one in the back carbon, and that's the one I'm going to draw the circle. So you are looking through this sigma bonding shown up here, okay? And then this one, I will see that, okay, this methyl here and this ethyl here is on the same plane. So that means the ethyl and the methyl are on the same plane. So this is what I'm going to write, CH3. Once this is being defined, chlorine is moving away from the side, so you can see that, okay, back carbon, chlorine is attached to here, and then I guess the leftover is on hydrogen. And then I am going to consider this. Okay, so like I said, this is on hydrogen that has to be react, and this is a hydrogen, and this is a leaving group. You see that there is a lot of BG kind of the reaction. Okay, so the base supposed to react here, but then this is a leaving group, right? And as a leaving group. But your assessment in this scenario is this is too crowded, right? So that's the things that making this scenario not happy. Not happy. No, this is a happy, right? This is a scenario that is not happy because you're kind of make things a lot of busy on this side. So what can happen is the rotation along sigma bonds. Okay, so we are talking about bond rotation here, as I trying to show. You see the bond rotation, so they can rotate this bond, and the sigma bond rotation. And then what's going to happen is I am going to keep my bond in the back to be the same. So this methyl rotation is always a kind of the relative one. So I'm going to keep this one as same. But now in the front carbon, this one, I am going to rotate. Okay, I'm going to rotate to this direction. And when I do that, now the hydrogen is here. And as a consequence, methyl is at the bottom now. And then what happened? The ethyl is going to be on this side, right? Can you guys see that? The rotation of a carbon-carbon bond and through where the Newman projection, right? Newman projection has been seen. I rotate that. And then let's do the color coordination once more. This is a leaving group. This is a proton group to be taken by the base, and this is a leaving group. They are on the anti-side. Right? Opposite side, less crowded. Or in a way, less steric hindrance. Okay, this is organic chemist term that they are liking it. So what that means is now you're looking at this unhappy scenario where the base coming in is too crowded. The situation is changed now. Okay, so then now if you look at the base, hey, I'm the base. I'm looking for trying to take the hydrogen. Okay, this one is good. And then let me give this one to the this bond as forming a double bond, and then let me kick this one out. So action is now, you can see that, let me be a little quote-unquote artistic. So the action on this side, right, the approaching side, and the leaving side is kind of separate each other, right? So therefore, this is what they call anti, and that's the one that they prefer. So then this is essentially what is a key portion in the textbook, or the answer key was provided from the textbook suppliers. And then having said that, now I'm going to using this space as a one. Okay, I know the double bond is being formed, right? So in a way, if you want to color coordinate it, I'm talking about the double bond. Red is the one in the behind, and the blue one is in the front. And then I'm going to say, okay, the back one, when they form, it looks like CH3 methyl and the ethyl on the same side, right? You see this? They are on this side together, and this side, methyl and hydrogen on the other side. So hydrogen is here, and the methyl is here. Okay, so this will be the product, which is different, right? If you look at here, they are not the same. So this is actually wrong product. If I kind of put it up here. So what is a correct product? Correct product is essentially CH2 carbon double bond with a methyl, CH3, and hydrogen. So this is the correct product, where now you can see this. Methyl, the opposite side, and this is what we call the trans isomers. Okay, and there is another notation that I actually put it on the YouTube on a lengthy version of solution number 2. And if you follow the E versus Z isomers, okay, it's Eingegangen means the opposite side, zusammen means the same side in the German. And if you look at that priority, this one is a bigger. Ethylene is bigger than the methyl. Methyl is bigger than methyl. And methyl is bigger than hydrogen. So they are on the same side. So this is essentially zusammen isomer. Okay, so it's one of the rare cases actually trans is at the same time call it as a zusammen, and this is pretty rare here, but that's the answer. Okay, so this is an answer, and you need a sort of the three-dimensional consideration of the molecule for the abstraction, and the base has to approach from the other side where the leaving group of this chlorine, the leaving group has to be on the opposite side, so that is a less crowded, right? So there's less steric hindrance. So here's a question that I have solved it, and then now I'm going to move on to this. If I can solve, I have essentially provided the table for you. Here you see the table here, and I wanted to talk about the lone pairs, the compound with the lone pairs, right? And you can see that there are compound with a nucleophile. There's a compound with something called a base. And these are both we looking for something that is positive. One is looking for the carbon that is positive, that's a nucleophile. Base is looking for the hydrogen that is partially positive, and they're trying to take it away, and then finish the acid-base reaction. Okay, so before I go, I have this quick question that I want you to essentially challenge you. So let me pick on the SN1. So I'm going to ask you, let's suppose that this is an SN1 reaction, and I want to figure out which one is the fastest. Okay, I'm taking, say, methyl iodide or the tertiary butyl iodide. Which one will be the faster in terms of if the reaction were to happen in an SN1? You guys can use a chatting box to answer that, put your question in a more private format. You guys can say, I don't know. It will be great, but have you ever thought about this? SN1. Okay, I'm waiting, but I can move on. Okay, you think about it, and why am I asking this question is SN1 reaction is involved with this kind of the alkyl halide. Right? These are the alkyl halide, and SN1 generate carbon carbocation, and we want something that more stable. Right? More stable carbocation is what we are looking for. So what you can, as for the SN1 reaction, right? SN1 reaction, you should consider that this one must generate methyl carbocation, and if it is an SN1, because the problem says so, and you are generating this as a tertiary butyl carbocation, right? Which is more stable carbocation? That one you guys can say then, right? A or B? If you do not know, then we are in trouble, right? So which is more stable carbocation? The one that tertiary carbocation, am I right? So therefore, this is more stable. So therefore, which is the fastest? The answer is B. Okay, so I think that everyone is on board with me, and if you can, you guys can see my hands, right? Yes, okay, good. Okay. Sometimes I made a mistake, and then I'm just talking without giving you any kind of right information. So let me switch the gear to, okay, what about the second one, right? The blue problem. Let me concentrate on SN2. So SN2 is, in a way, we are talking about carbon, and let's say it's iodine, so that's a leaving group, and this is an electronegative here, right? So electronegative here, so there's a little bit positive, and then you are looking for the nucleophile, and this is a case of strong nucleophile trying to push and trying to go into the opposite side and trying to force this one to be a leaving group. So that's why you are having these two entity involved, right? For this compound alkyl halide and the nucleophile essentially colliding each other with the inversion of the stereochemistry, right? So in a way, for answer this question, what you have envisioned yourself is, for answer this, which is the fastest, you should think about drawing the nucleophile, trying to attack here, right? You think about the nucleophile, trying to attack here. Which one will be faster? Which one will be, in a way, easier? Can you guys think about that, right? And this is where what is called the steric hindrance is coming into a play. This carbon is partially positive. This carbon is partially positive because electronegativity here by the iodine, and which is a leaving group. But this one is essentially kind of the hydrogen is surrounding the carbon here, right? So hydrogen is surrounding this carbon, whereas this carbon that's supposed to make a bond with a nucleophile is surrounded by this bulky CH3, right? So it's like shooting a bird in the surrounded a lot of big thick bushes. So okay, that's the case B, and so therefore this one we are saying that this one experiencing steric hindrance. Hindrance means you're slowing down, right? So it's a slow down the reaction. So therefore, which is the fastest? In this case, is A is the answer, right? Because this one is not much steric hindrance. So have you guys heard about Dr. Ma talking about steric hindrance, right? And the crowding. So make sure that you understand the differences between these two. And then when the nucleophile is attacking it, this is obviously SN2 reaction. And I can put the distinction between those two. So let me kind of finish up this table here. Okay, so when you think about the nucleophile, we are using the word nucleophile as this, whereas a base is we are using something like this, right? So that's a notation that we are using it. And when you have a strong nucleophile, when you have a strong base, it is so I'm kind of solving in a different way than other sessions. So when they are strong, it is essentially kind of inducing it. So nucleophile is a part of the reaction, so it is a bimolecular. Okay, and so therefore, and then this is a nucleophile, so this is a nucleophilic substitution, and it's a base, so E2 is their reaction type, right? And when they are something as a weak nucleophile, so that means, in a way, you need to have a good leaving group, okay? And they're supposed to form the carbocation formation first, right? So this is the same thing, good leaving group, and they form the carbocation. In this case, you can think about forming the carbocation, forming this trigonoplanar structures, and upside and the downside can happen at the same time, whereas this one is SN2 is essentially inversion, right? So this is more like a stereochemistry structure-wise was an inversion, right? Whereas the SN1, which is a weak nucleophile, which is on 1 nucleophilic substitution, this will be a sort of the both up and down mixtures, right? Because of the nucleophile can react from the top or the bottom once they form the carbocations, as shown as I shown here, and this is also true for the for the understanding the structure of this chemistry. And also when you see the base, and this is okay, so this is a weak, so you have to wait until the carbocation made it, and then you form the double bond here. And because of the formation of that carbocation, you can see what is called the hydride shift and methyl shift, and carbocation rearrangement. You should also consider that. And so those are the two aspects that you need to consider when you are dealing with a unimolecular reaction. And this is an essential formation of carbocation, which is more like a flat morphologies, and then later they are going to make a bond with a nucleophile. Okay. What about the reaction kinetics? And then this is a reaction kinetics because it's a bimolecular. Once you figure that out, this is an SN2, is a reaction rate, and then we call Rx and Nu. Okay, both concentration has to be, those two compounds has to collide each other, so the concentration depends on the both terms, where the Rx is essentially alkyl halide, just like I shown up here, right? So this is an alkyl halide, methyl iodide, or tertiary butyl, so that's an R with an X, which is a halide, and that's the leaving group. When it's a unimolecular nucleophilic substitution, rate determining step is just depending on dissociation of the alkyl halide by losing the halide group. So it does not depend on the nucleophile concentration. What about the E2? So same thing, Rx, because elimination. So you should say the base, not the nucleophile, because of the elimination, you are losing the proton, forming the double bond. So this is a base you needed here. And this is, once again, is the same. The base concentration doesn't matter for the elimination reaction. So those are something that I want you to keep that in mind here. And before, for the last point that I wanted to make, and because I'm running out of space here, but let me just trying to make a little point here. Okay. So you talked about carbocation arrangement, right? So if you probably the most common example is when you see the secondary carbocation, there is a hydride shift or a methyl shift to make it tertiary carbocation, right? The example of tertiary carbocation is this, right? So that's what they want to prefer to form. But if also remember that this is not only the stable carbocation form. If you have a benzene group is attached to here. So this is what they call the benzyl carbocation. This is very stable too. And the reason is because this is an induction effect, right? The electron donating group effect. Whereas this one is actually this double bond can form change the position, and the positive charges can be moved around from delta plus here, delta plus here, delta plus here. Okay? So the benzene group is a way that kind of stabilizes the one. So the benzyl, I think what I mean by this is a benzyl. Carbocation is very stable. Okay, very stable. So remember to develop your eyes when you see the benzene with a carbon attached. Okay, it has to be the aromatic group attached to this one is a very, very stable carbocation. The other one that is also you will learn in the organic chemistry is if you actually not as effective as a double benzene group, if you have a double bond with a carbocation right here. Okay, and this is what we call the allyl carbocation. This also just not even 3 double bond with this one itself, right? This double bond connected to the carbocation is also good enough to stabilize this, and the same kind of idea that, okay, they can kind of form the double bond here, they can develop the partial positive charges. If they can spread the charges around, they can be a stable one. So what I mean by this is a final point, which is here, the carbocation arrangement. Think about not only the tertiary carbocation, but benzyl carbocation or allyl carbocation. If they can move the hydrogens or methyls around, if they can form this, they will form that way. Okay, so that's my other points that I want to mention here.